Alright, exercise 56. This one is about Hilbert spaces, and Hilbert spaces are nice, so this one is really nice. Now, we're going to do a series of claims here, and then we're going to, after we've finished with all these claims, we're going to give the proof. So, my first claim, ePerp is a closed subspace of H. For, then I get to use a great word here, subspaceness. If X and Y are in ePerp and lambda is a complex number, then for all Z in our set E, the inner product of X with Z is equal to the inner product of Y with Z, which is equal to 0. So, if we look at the linear combination, inner product with Z, this, if we just break it up, Z plus, let's see here, it's linear in the first variable and conjugate linear in the second variable, so this is just the lambda comes out by itself with no conjugate. And this, well, we're taking 0 plus something times 0 is 0. This holds for all Z and E, and so X plus lambda Y is in ePerp. So linear combinations of things are in ePerp, and so it's a subspace. For closedness, which is a little less neat of a word, but whatever. If we have a sequence xn in ePerp such that xn converges to some x which belongs in H, then for any fixed y in E, we have xn y equals 0 for all n in n. So by continuity of the inner product, xy is equal, that was weird. So the limit as n goes to infinity of xn y, because you write x here as the limit of the xn's, but then you can bring that limit outside by continuity. But then this is just the limit of a sequence of 0, so it's just 0. This holds for all y in E, so x is in ePerp, and thus ePerp is closed. I've left out the word is, so this isn't technically a sentence, but at least I got it all to fit on that line. And so ePerp is a closed subspace. Next claim. I claim that for any arbitrary subsets of H, if A is a subset of B, then bPerp is a subset of aPerp. Let's prove this. If A is a subset of B, let X be in bPerp. Then, well, that should be a 2. Then for all y in B, the inner product of x and y is equal to 0. So, well, that means that for all y in A, xy is equal to 0. So x is in aPerp, and this holds for everything in bPerp, and hence B perp is a subset of A perp. Wow. Another one. Got to fit on the last line. Third thing. I claim E is a subset of E perp perp. So let X be an E. Then for all Y in E perp, we have ZY equals 0 for all Z in E. So in particular, well, X is an E, so we can write inner product of X with Y equals 0. This holds for all Y in E perp, and so thus X is in E perp perp, so E is contained in E perp perp. Yeah, there we go. I might fit this all on one screen. Let's see. I next claim that the closure of E perp perp is contained in E closure. So we will prove that, let's see here, E closure perp perp complement contains E closure complement. And this implies that. So suppose X is not in the closure of E. So let's see here. Since E is closed, because it's a closure, H is equal to, here, is a closed, let's see here, subspace, right? I think it just needs to be closed. If it needs to be a closed subspace, then it's also a subspace. I'm blanking on the details here. But the point here is that we can write script H as E closure direct product with E closure perp. So then X Z inner product is equal to Y plus Z Z. Right. And so then this is equal to YZ plus ZZ just by linearity, but then inner product of Y with Z is 0 since Y is in E closure and Z is in E closure perp, and so this is just Z squared. And this is greater than 0 because if Z were not greater than Z, the only way for Z to be equal to 0, the only way for this norm to be equal to 0 in Hilbert space is for Z to be 0, which would imply that when we write, oh man, I missed something huge here. So let's see here, X equal Y plus Z. So this X equals Y plus Z, Y is going to be in E closure, and Z is going to be in E closure perp. And so once we define it that way, then what we're doing is we're taking this inner product here with X and Z in particular, and because X is equal to Y plus Z, we just do this here, and so blah blah blah. So now look, if z were if z were equal to 0, then we just have x equal y. But y is in E-closure, so that would mean x is in E-closure, but we defined x to not be in E-closure. So z must be non-zero, and so this thing is greater than 0. And hence, in particular, x is not in E-closure perp. Because if it were, then this inner product would have to be 0 for all z in E-closure perp. But it's not for this particular value of z. And so this confirms that E-closure perp complement contains E-closure complement, which implies that E-closure perp is contained in E-closure. So 5. Now we can do the proof. Finally, E is contained in E-closure, obviously. This implies E-closure perp is contained in E-perp. That's just number 2. Then we do this again. E-perp is contained in E-closure perp. So E is contained in E-perp, and that was number 3. And this is contained in E-closure perp, and that's what we just proved. And so, but this is equal to E-closure by 4. But E-perp is closed. And that's by 1, because E is any subset, but then E-perp is a closed subspace. But then E-perp is also a closed subspace. And so it must be that E-perp equals E-closure. Because as we see here, E-perp is a closed subset of the closure of E. And by definition, that means that E-perp is the closure of E. But then E-perp is the smallest closed subspace of H containing E. And this completes the proof.